Alright, let's talk about Raoult's law. A problem involving Raoult's law will ultimately ask you to find the vapor pressure of a solution, not of the solvent, but of the actual solution. And in order to solve this type of problem, you need to be given the vapor pressure of the pure solvent. And notice here that we have methanol, we have the information of the density, the molar weight, and we also have the vapor pressure of methanol, implying that that's the solvent. And right here we have 50 grams of quinacridine and the molecular weight is given right here. Alright, now if you're unsure as to what is the solvent and what is the solute, simply convert both of them to moles. Whichever is in greatest amount in moles is the solvent. Whichever is in least amount in moles is the solute. And technically speaking, that's what we're going to do here. I'm going to take the 50 grams of quinacridine, which I'm abbreviating with Q, divided by the molar mass of quinacridine to get to moles. Upon carrying out the calculation, 50 divided by 137.23, we get 0.364 moles of quinacridine. Now we do the same thing with methanol, but here we have 50 mLs, so we first need to use the density to switch over to grams. mLs on the bottom, grams on top, cancel out the mLs, and now we use the molar weight to switch over to moles. So divide by 32.04 grams, that's equal to 1 mole. The grams of methanol cancel out, and now you have 1 mole of methanol on top, which upon doing the calculation, we find out that this is 1.24 moles of methanol. So if up until this point you didn't know which was the solvent and which was the solute, now you know. Because methanol is present in 1.24 moles, quinacridine is only present in 0.364. Since methanol is greater than quinacridine, methanol is the solvent, quinacridine is the solute. Alright, now the other thing is that quinacridine is not an ionic salt. We know that because we're not ending with chlorides, fluorides, sulfates, nitrates, none of that stuff. This is, something you haven't even heard of until now. So this is most likely not a covalent molecule. So the value of I, or the number of ions, is simply 1. There is no ions, right? It's just a molecular, covalent molecule. Alright, now what we do is we calculate the mole fraction of the solvent. Okay, so we divide the 1.24 moles of solvent by 1.24 plus 0.364, which is 1.604. So divide 1.24 by 1.604, and you end up finding out the mole fraction of the solvent, which in this case is 0.773. Okay, now we get to use Raoult's law. Vapor pressure of solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent, which we know from the data right here to be 0.128 atmospheres. So we multiply that vapor pressure by the mole fraction, which is 0.773, and that yields the vapor pressure solution, which indeed is lower than the vapor pressure of the solvent. Alright, now let's do a similar yet slightly complicated example. Now instead of using quinacridine, which was a covalent molecule, let's use lithium chloride, which we know for a fact to be ionic. Alright, so we convert the mass to moles like we did before, so divide the 5 grams of lithium chloride by the 42.39 grams of lithium chloride per mole. That will tell you the moles of lithium chloride, but for every lithium chloride mole that you have, you end up with 2 moles of ions. So notice the conversion factor I'm using right here to account for that. You will only need to do this for Raoult's law. So don't actually convert to moles of ions for the boiling point elevation formulas, freezing point depression, or osmotic pressure. Those ones already have the number of ions incorporated in the equation. But Raoult's law does not, so we need to do this step. Okay, so we're dealing with 0.236 moles of ions. Alright, we already know that for methanol, we have 50 mLs. We're still using the same density, the same molar weight. So we know that we have 1.24 moles of methanol. So add the 1.24 with the 0.236, excuse me, and you will get 1.24 divided by 1.476 as the mole fraction of the solvent, which in this case is 0.840. Using, once again, Raoult's law, we plug in the mole fraction 0.840 multiplied by the vapor pressure of the solvent, the pure solvent, 0.128 atmospheres, and find out that the vapor pressure of the solution is 0.108 atmospheres. All right, one more example. This one kind of takes us a step further. So we see what happens when we dissolve a solute that doesn't have a vapor pressure into solution. But what happens if you actually use a solute that, in addition to the solvent, happens to also be volatile? A typical case would be when you mix two liquids together, such as ethanol with methanol. Each one of those two components will have a vapor pressure. And so what happens is that each vapor pressure will contribute to the total pressure of the system. But each vapor pressure can be approximated, because we know that the total pressure is going to be equal to the partial pressure of methanol, and in the other case the vapor pressure of ethanol. But since they're both dissolving each other, they're changing their overall vapor pressures. And so the vapor pressure of methanol can be approximated by multiplying it with the mole fraction of ethanol. But that of ethanol will have to be multiplied by its own mole fraction. So here you basically take the values of the pure methanol and the pure ethanol in terms of the vapor pressures and multiply them by the corresponding mole fractions. When you add them together, that will give you the vapor pressure of the solution. And technically what happens is that as you start increasing the amount of one substance, your vapor pressure may decrease to some value. The other one may also increase, and ultimately the summation that it's happening right here is that you're basically going to look at this overall addition. So this line right here, which is the addition of the blue line with the pink line, is the vapor pressure of the solution. And what I want to show you is a typical experiment that makes this happen. This is called a fractional distillation, where we have the flask right here containing your initial substances. And technically a graph shown right here is kind of what happens in terms of moving the solvent across this column. So you have your mixture initially in this flask, ethanol, methanol, which could be maybe 90% one thing, 10% the other. And as you start heating up this liquid, the liquid evaporates and it goes up to this column called the fractional distillation column, which actually has some spikes going inwardly. And it's through those spikes that the gas that you generated condenses back to a liquid, but then that liquid re-evaporates and keeps traveling further up the column, recondensing, re-evaporating, recondensing, re-evaporating, recondensing, re-evaporating. And ultimately what happens is that you had an initial temperature T1, but as you go through this evaporation condensation cycle, you start decreasing the temperature until you get to the pure boiling point temperature of the second substance. And at that point, you're basically condensing the substance over here using cold water to ultimately collect it down here in this setup. So this is actually a pretty neat thing to do, although it can be a lengthy process when you do it in practice. Now, as I was telling you, the fractional distillation column has these spikes, and it's through those spikes that you actually undergo the process of purification of the substance. Initially, you had 90% of A, 10% of B. By the time you get to the next spike, it could be 60% A, 40% B, then 20% A, 80% B, and eventually you get to 100% B. So this is a means for you to separate two liquids from each other. It works in some circumstances and in others it doesn't, but it is a technique that we get to use in chemistry quite often. Especially if you do organic chemistry, you'll get to do this for sure in the laboratory section. Alright, now I'll stop the video right here, and on the next video we'll talk about the rest colligative properties.